In data science and machine learning, having a basic understanding of probability and probability distributions is an absolute requirement. And this video aims to provide you with an overview of what probability and probability distributions are, and should prepare the ground for a next video that will introduce the normal distribution, which is the most widely used probability distribution in data science. So let's begin by defining the term probability. Probability is usually denoted with the letter P. It's a number between 0 and 1 that indicates how likely an event is to occur, oftentimes within the framework of a random experiment, where an event is a set of one, many, and sometimes even 0 outcomes from a sample space containing all possible outcomes. So let's look at an example so that this definition makes sense. The event obtaining an ace when drawing one card from a deck of 52 cards is going to be 1 over 13 because the event obtaining an ace contains 4 possible outcomes. Since we have a total of 4 aces in the deck of 52 cards, we have the ace of spades, the ace of diamonds, the ace of clubs, and the ace of hearts. That gives us a probability of 4 over 52, which, if we simplify, gives us 1 over 13. That's a probability of 0.076, or a 7.6% chance of obtaining an ace when drawing this one card from the deck. Let me say it again. In our example, the random experiment consists of drawing one card from a deck of 52 cards. The sample space is the deck of 52 unique cards. Therefore, the total number of outcomes is also 52. But we have an even greater number of events because each and every outcome taken individually is an event. Then we have events that contain more than one outcome. For example, drawing an ace without any symbol specified contains 4 outcomes, and it will occur whenever we draw one of the 4 aces. The event King of Clubs contains only one outcome because the card King of Clubs is unique. Same thing for a 2 of Hearts. The event Drawing a Spade contains 13 outcomes. We have 13 spades in the deck. The event Getting a Red Card contains 26 outcomes because we have 13 diamonds and 13 hearts. The event Getting a Face Card contains 12 outcomes because each symbol has 3 faces, a king, a queen, and a jack. So we have a total of 12 faces in the deck, etc., etc. You get the idea. So let me recap. The probability of drawing an ace is 4 over 52, or 1 over 13. The probability of drawing a King of Clubs is only 1 over 52. The probability of drawing a spade is 13 over 52, or 1 over 4. It's a 25% chance of getting a spade when drawing a card from a deck. And if we generalize, we can say that the probability of a given event A is equal to the number of outcomes associated to this event A divided by the total number of outcomes in the sample space. In other words, P of A, the probability of event A, is the cardinality of event A divided by the cardinality of the sample space. And the term cardinality stands for number of outcomes here. As a side note, keep in mind that this method of calculating probabilities is valid only if the sample space contains a finite number of distinct and equally likely outcomes. In our example, the sample space is countable. We can count the number of outcomes. We have 52 outcomes, and these outcomes are equally likely. In other words, the probability of drawing any of the 52 cards is the same. It's 1 over 52. We've seen what a probability is. Let's now talk about random variables. A random variable is a function that assigns a numerical value to a given outcome during a random experiment. And to illustrate this definition, let's see a couple examples. Let's say that our random experiment is once again drawing a card from a deck of 52 cards with no repetition. So we draw one card only. And let's say that we win if we draw the King of Hearts, and we lose if we draw any other card that's not the King of Hearts. Then we need to encode these two possible results into numerical values so that we can do something with them mathematically. As you know, a computer or a machine learning algorithm cannot interpret textual data. So we need to turn King of Hearts into a number, or not King of Hearts into a number as well. And typically when we perform a random experiment that results in either success or failure, we represent success by 1 and failure by 0. So 0 and 1 are the two possible values for the random variable x. It's called a binary variable. X can take only two values, 0 when we fail, 1 when we succeed. Let's take a look at a second example. Let's say that our random experiment consists of rolling a die 3 times, and we want our random variable x to track the number of successes. Here, the success is going to be defined as getting an even face, and we want to count the number of even faces we obtain after rolling the die 3 times. As you know, a 6-sided die has 3 even faces. 2, 4, and 6 are even numbers, and 3 odd faces, which are 1, 3, and 5. So we have a probability of 3 over 6, or 1 over 2, of obtaining an even face each time we roll the die. And we want to count the number of successes after rolling the die 3 times. So we could roll the die 3 times and get 0 success. We could roll the die 3 times and get 1 success and 2 failures. We could roll the die 3 times and get 2 successes and 1 failure. Or we could roll the die 3 times and get 3 successes. So each time we roll the die, we get an even number. And these are the possible values for x. This set of possible values is called support, by the way. So x, after rolling 3 times the die, x could be 0, 1, 2, or 3. Now, why do we call the random variable x a function? Well, because it takes as input one of the possible outcomes of the sample space and outputs a number. The probability of x being equal to the King of Hearts becomes the probability of x being equal to 1. Something you should be aware of is that there are 2 types of random variables. We have discrete random variables and continuous random variables. You know, a random variable is discrete when you can count the number of outcomes in the sample space. In other words, when the number of values it can take is finite. Here's a few examples. Number of deaths per day in a hospital, number of dice rolls to get to 6. The number of deaths per day in a hospital cannot be 2.5. It can either be 0, 1, 2, 3, or more, but it's always going to be expressed with whole numbers, not with decimal numbers. And you know, a random variable is continuous when the number of values it can take is infinite, when its support is infinite. Here's a few examples. Gas mileage, height of adult females, marathon finish time. If we take gas mileage, it's going to be expressed in decimal form with potentially an infinite number of values after the decimal point. So keep that in mind. So far, we've talked about probabilities and random variables. Let's now focus on probability distributions and see what they are. There exist many probability distributions, and since there are discrete random variables and continuous random variables, we're going to also have discrete probability distributions and continuous probability distributions. In fact, we say that a discrete random variable follows a discrete probability distribution, and a continuous random variable is associated with a continuous probability distribution. Let's get back to the first example we looked at earlier. Our random experiment consists of drawing one card from a deck of 52 cards with no repetition, so there's only one trial. The random variable x is going to take the value 1 if we draw the King of Hearts, and the value 0 otherwise. In other words, success is encoded as 1, and failure is encoded as 0. If the random experiment results in either success or failure, if we know the probability of success, we can also calculate the probability of failure. In this situation, success and failure are two mutually exclusive outcomes that cannot happen at the same time. Therefore, the sum of these two probabilities, the sum of the probability of success and probability of failure, is going to be equal to 1. And if the probability of success is some number between 0 and 1, we can deduce that the probability of failure is going to be 1 minus the probability of success. I hope this makes sense. And it turns out that we know the probability of success. The probability of drawing a King of Hearts is 1 over 52. In other words, it's a 0.019 probability, or 1.9% chance of drawing a King of Hearts. Therefore, the probability of failure is 1 minus this value, which gives us a probability of 0.981, or a 98.1% chance of failing, of drawing any card that's not the King of Hearts. And that, my friends, is the distribution of this particular random variable x. An important side note here is that the shape of this distribution is going to change if we change the probability of success. Suppose we define success as drawing a spade, any spade. Then the probability of success is going to increase and the probability of failure is going to decrease, because the probability of drawing a spade is 13 over 52. So we have a 25% chance of drawing a spade. And this distribution is called the Bernoulli distribution. We say that x follows a Bernoulli distribution of parameter p, where p is the probability of success. Most of the time, a specific probability distribution is going to have 1, 2, or more parameters, which must be known, as well as an associated function that allows us to calculate the probability that the random variable x is equal to each of its possible values. In this case, this function is called a PMF. PMF stands for probability mass function, and that's what you're going to have when you deal with discrete probability distributions. And when you're dealing with continuous probability distributions, you're going to have a PDF, a probability density function, associated with the specific probability distribution you're using. So the PMF for the Bernoulli distribution looks like this, and it says that the probability of capital X, which is the random variable x, being equal to little x, which is one of its possible values, in this case it's 0 or 1, is equal to p, the probability of success, raised to the power of little x, times 1 minus p raised to the power of 1 minus x, or little x. Suppose that little x is 1, then p raised to the power of 1 is p. 1 minus p raised to the power of 0, because 1 minus 1 is 0. Any number raised to the power of 0 is 1. So this whole part is going to be 1. P times 1 is just p. And usually when we use the Bernoulli distribution, we use these two equations. We know that the probability of success is p. It's given to us. And the probability of failure is just 1 minus p. If we replace here the little x by 0, you're going to be left with 1 minus p. Let's move on to a second example and have a look at another prominent probability distribution, the binomial distribution, which is closely related to the Bernoulli distribution. Our random experiment consists of rolling a die 3 times, so there's going to be 3 trials. The random variable x is going to be the number of successes after 3 trials. Success here is defined as rolling a 2, a 4, or a 6, so rolling an even number. And this is what the distribution of this random variable x looks like. This is the binomial distribution. On the x-axis, we have the possible values for x. So x can be 0 for 0 success after 3 trials. It can be 1 success, 2 successes, or 3 successes. And these are the probabilities associated with each possible value of x. So the probability of having 0 success after 3 trials is 12.5%. The probability of having 1 success is 37.5%. Same for 2 successes, and there's a 12.5% probability of having 3 successes after these 3 trials. We can say that x follows a binomial distribution with parameters n and p, where n is the number of trials and p is the probability of success. The probability of failure is going to be 1 minus p again. And the main difference between the Bernoulli distribution, which we saw earlier, and the binomial distribution lies in the number of trials. For the Bernoulli, we only have 1 trial, and the binomial is in fact a series of n independent Bernoulli experiments. Any experiment that results in either success or failure is a Bernoulli experiment, and the binomial is a series of n independent Bernoulli experiments. That's why they are closely related. We often hear that the Bernoulli is a special case of the binomial distribution where n equals 1. The formula for the PMF of the binomial distribution looks like this. The probability of x being equal to k, where k is the number of successes after 3 trials, is equal to n choose k times p raised to the power of k times 1 minus p raised to the power of n minus k. The formula looks scary, but in reality, it's a pretty simple calculation. We're going to use this PMF to demonstrate how we get these probabilities that you're seeing on the chart. Let's do it together. In our example, a success is defined as rolling a 2, a 4, or a 6. Therefore, the probability of success is 3 over 6, which is equal to 1 over 2. So we have a probability of 0.5, a 50% chance of obtaining a success each time we roll a die. K is the number of successes after 3 trials. N equals 3. We have 3 trials. Here we have the formula where n choose k is equal to n factorial divided by n minus k factorial multiplied by k factorial. If you don't know what n factorial is, hold on, we're going to see that in a few moments. Let's insert the actual values into this formula. Here I'm going to calculate the probability that x equals 0 success. So k equals 0 success. K is the number of successes, remember. But in order to get the full distribution of the random variable x, we need to compute a total of 4 probabilities. So here I'm going to compute the probability, the first one, and you can repeat the process to get the full distribution. So the probability of x being equal to 0 success is 3 choose 0 multiplied by 0.5 raised to the power of 0 multiplied by 0.5 raised to the power of 3, where 3 choose 0, so this part, is equal to 3 factorial divided by 3 factorial times 0 factorial. And this gives us, so 3 factorial is 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1, etc., etc. You get the idea. And that gives us 6 in the numerator. In the denominator, we have 3 factorial, which is 6, times 0 factorial. And 0 factorial is equal to 1. So it sounds odd that 0 factorial is equal to 1. But if you want the proof, just check it out on the internet. And the whole thing, so 3 choose 0 is equal to 1, because 6 divided by 6 is equal to 1. So let's keep going. This whole thing is equal to 1 times 0.5 raised to the power of 3. We just saw that 3 choose 0 is equal to 1. 0.5 raised to the power of 0 is 1. Any number raised to the power of 0 is equal to 1. So we're left with 0.5 raised to the power of 3, which is 1/8 or 0.125. The probability of x being equal to 0 success is 0.125. That's what we observe on this chart. And again, if you want to get the full distribution of the random variable x, you need to compute 3 more probabilities. The probability that x is equal to 1, 2, and 3. Now let's make a quick comparison between discrete and continuous distributions. As I said earlier, if the random variable is discrete, we're going to have a discrete probability distribution. And if the random variable is continuous, we're going to have a continuous probability distribution. The function that allows us to compute each and every probability in a discrete distribution is called a PMF, probability mass function, whereas the function that allows us to compute the probabilities in a continuous probability distribution is called PDF, probability density function. One of the main differences between these two types of distributions is that with discrete distributions, we can obtain the exact probability for each and every possible value of x, whereas with continuous distributions, we cannot. We cannot obtain the exact probability for a given value of x. Since a continuous random variable can take an infinite number of values, the probability of observing any of these values is very, very close to 0. It's infinitely small. Therefore, we say that it is 0. If we take as an example the height of adult males and females expressed in centimeters, we can say that the probability of observing someone who's exactly 173 centimeters tall is 0. So what can we do? Well, we could compute the probability that someone falls within a given range. For example, we could calculate the probability that someone is between 168 and 173 centimeters tall, or we could calculate the probability that someone is less than a given height or above a given height. Know that for continuous distributions, the probability is usually expressed as the area under the curve, and the total area under this curve is equal to 1. Continuous distributions can also be represented with histograms, where we're going to calculate the area of bins. Here we have bins with a width of 5, and we calculate the area of one or several bins by multiplying its density by its width. So the probability of someone falling between 163 and 168 is going to be equal to the density of this bin times its width, which is 5. That being said, how do we actually compute the area under the curve for a given range or a given interval? Well, we know how to compute the exact area of a square or of a rectangle, but how do we do so for a curvy geometric figure? Well, we cannot obtain an exact area. We can only approximate this area by placing very thin, very narrow rectangles under the curve. In fact, we're going to place infinitely thin rectangles under the curve, and the sum of the areas of all the rectangles under the curve is going to be equal to 1. And if we want to calculate the area under the curve, so the probability for a given range, we're going to add up the areas of all the rectangles that fall within this particular range. So we're going to integrate the areas of the rectangles that fall within this range. This is called integration. To be precise, we're going to use what's called a CDF, cumulative density function, to calculate the area under the curve for a given range. So if we take back our example, so the heights of adult males and females, let's say we want to find the probability of observing someone that is less than or exactly 173 centimeters tall. We're going to use the CDF, and the CDF is going to add up all the areas of the rectangles that fall within this particular range. And it's going to return the probability we want. As a side note, know that there exist CDFs for continuous distributions and for discrete distributions. Now, what if we want to find the probability that someone is between, let's say, 163 and 173 centimeters tall? Well, we need to first calculate the probability that someone is less than or exactly 163, and that would be the yellow hatched area under the curve, and we would pick this probability and subtract it from the first probability we calculated, and we would obtain the area, the white hatched area under the curve, which is the probability of someone being between these two values, between these two heights. Finally, suppose we want to find the probability that someone is taller than the average height. The average height is 173. We still need to use the CDF, but the CDF starts accumulating probabilities from minimum height all the way to a given value. So how can we use the CDF to calculate, to compute probabilities that start from the average height, from a value that's in the middle of the distribution, all the way up to maximum height? Well, we need to subtract. We know that the total area under the curve is 1. So we need to subtract the red hatched area, the red hatched probability from 1. And that will give us the area under the curve to the right of the average height. So the brown hatched area is equal to 1 minus the red hatched area. And that's how we calculate probabilities when using continuous probability distributions. So let's recap real quick. For discrete probability distributions, the PMF, the probability mass function, is used to compute the probability of observing each possible value of x. So in this example, the possible values of x are 0, 1, 2, or 3 successes after 3 trials. And the CDF is used to compute the probability that the random variable x takes a value less than or equal to one of its possible values. For example, the probability of obtaining at most 2 successes after 3 trials is equal to the probability of x being equal to 0 success plus the probability of x being equal to 1 success plus the probability of x being equal to 2 successes. Note that I'm adding up these probabilities because these are mutually exclusive events, but that's not always the case, as you will see in a future video when we tackle conditional probabilities. And in this example, the probability of x being less than or equal to 2 is 0.875. For continuous probability distributions, we know that we place a very large number of rectangles under the curve so as to approximate the area under the curve. And all the rectangles have the same width. They have a very, very small width, a tiny width that's generally denoted as dx. But these rectangles don't have the same height. A rectangle that's going to be placed here in the middle of the distribution is going to have a bigger height than, let's say, a rectangle that's going to be placed here to the left. So we need to know the height of each rectangle in order to compute its area. And that's the role of the PDF, the probability density function, that gives us the height or probability density of the curve or the rectangle at a given possible value of x. It doesn't give us the probability of observing this particular value of x. It gives us the height of the rectangle at this location, the height of the curve. And the CDF is used to approximate the probability, so the area under the curve, from the lower limits of the distribution all the way to a given value of x by adding up the areas of all the rectangles that fall within this particular interval. Now let's talk about some other prominent discrete probability distributions. Let's begin with the hypergeometric distribution. The hypergeometric distribution is used to calculate the probability of having k successful draws in a series of n random draws without replacement, where a successful draw is defined as an item with a specific characteristic drawn from a finite population of size capital N that contains exactly a items with that characteristic. And we say that the particular random variable x follows a hypergeometric distribution of parameters n, capital N, and a. So we have 3 parameters for this distribution. And the PMF, since this is a discrete distribution, it has an associated PMF that looks like this. So this is the PMF of the hypergeometric distribution. And to illustrate what I just said, let's take an example. Let's say we want to find the probability of drawing k aces in 2 draws from a deck of 52 cards without replacement. So we're going to draw 2 cards, and we're not going to put them back into the deck. And we want to find the probability of obtaining 2 aces in these 2 draws. Now understand that in this particular scenario, the hypergeometric distribution is going to be composed of 3 probabilities only. We're going to use this PMF to calculate the probability that x equals 0 successful draw, the probability that x equals 1 successful draw, and the probability that x equals 2 successful draws, where a successful draw is defined as obtaining an ace. And we have 2 draws, so in 2 draws we can get a 0 ace, 1 ace, or 2 aces. So the probability of x being equal to k is equal to a choose k times capital N minus a choose lowercase n minus k, and the whole numerator is divided by capital N choose lowercase n. Let's keep going with our example so that this becomes crystal clear for you. Let's say that we want to find the probability of getting two aces in two draws. So in this case, k equals 2. N equals 2, so n is the number of draws. We have two draws. A is the number of cards that satisfy the specific characteristic, and in this case, the specific characteristic is a card being an ace, and we have a total of 4 aces in the deck, so A equals 4. And capital N is equal to 52, which is the total number of cards in our deck of cards. And when replacing the letters in the PMF with the actual values, we get this. So the probability of x being equal to 2, so 2 successful draws, 2 aces, is equal to 4 choose 2 multiplied by 48 choose 0, and the whole numerator is divided by 52 choose 2. And when calculating this, we get a very small probability. We get a probability of 0.0045 of drawing 2 aces in 2 draws. So it's a 0.45% chance of getting these 2 aces. And last but not least, we have the Poisson distribution, which is used to compute the probability of observing exactly k occurrences of an event within a given time interval or over a surface area based on an average number of occurrences lambda. We say that a particular random variable x follows a Poisson distribution of parameter lambda. So the Poisson distribution only has one parameter, lambda, and this is what the PMF of the Poisson distribution looks like. Remember that the Poisson distribution is a discrete probability distribution, and discrete probability distributions have an associated PMF, whereas continuous distributions have an associated PDF, probability density function. It's always good to repeat. Repetition is part of the learning process. So the PMF of the Poisson distribution says that the probability of x being equal to k occurrences of an event is equal to e raised to the power of negative lambda multiplied by lambda raised to the power of k, and the whole numerator is divided by k factorial. Again, let's take a look at an example so that you understand what the Poisson distribution is used for. Let's say we want to find the probability of observing exactly 10 airplane crashes in a year, given that the average number of crashes is 5. So in this scenario, lambda is equal to 5. So lambda is the average number of airplane crashes, and k is equal to 10. So the event here is the airplane crash. K is going to be the number of airplane crashes, and the time interval is equal to 1 year. So let's find out what the probability of observing exactly 10 airplane crashes in a year is, given that the average number of airplane crashes in the world in a year is equal to 5. When we insert these values into the formula for the PMF, we get the following probability. We get the probability of x being equal to 10 airplane crashes is equal to e raised to the power of negative 5 multiplied by 5 raised to the power of 10, and the whole numerator is divided by 10 factorial. In this PMF, the number E, which is called Euler's number, is equal to 2.71828, and there are other digits after the decimal point, but we usually stop there. Just know that the number E is a very important number in math, and when we compute this PMF, we get a very small probability. So the probability of witnessing 10 airplane crashes in a year when the average number of crashes is 5 is just 0.0181. In other words, it's a 1.81% chance of witnessing 10 airplane crashes. Note that when lambda and k or both are very large numbers, if you're using a basic calculator, you're going to get an overflow. So let's say that k is 1000. We're going to have in the numerator 5 raised to the power of 1000, and in the denominator we're going to have 1000 factorial, and these two are very, very large numbers that a basic calculator cannot handle. So you're going to get an overflow if you're using a basic calculator, if the values of lambda or k or both are large. This is inevitable. You're going to get an overflow. So you should use the programming languages R or Python instead, because these come with math packages that can handle these types of calculations. This is the end of the video. If you enjoyed it, please subscribe to my channel, like the video, comment, or even better, share it with other people who are interested in data science. I would really appreciate it. Again, thanks for watching and see you next time.